Okay, actually my plan is, everybody is standing, okay? My plan actually is initially, I want to show you how you can import a DXF file to set up the grid. And I also want to show you, I'll use this. But anyway, and how you can create a model like that using the AutoCAD file that you have. Yes. The key, we will explain later, the key is you must prepare your AutoCAD file in a reasonable manner. If you have problem, usually is you have not prepared your AutoCAD file nicely. But if you can understand this, then in many cases, you can generate things very, very quickly based on a series of AutoCAD drawings that you have prepared. Yeah. So we will skip this for the time being. I will focus on some other thing. Yeah. And this particular case is showing you how to create a non-prismatic section. And you will have a case, for example, you look at a portal frame or whatever, yeah, at the end you may need to change the profile. So it's not prismatic, not constant, right? We have a means to generate these kind of sections from the standard string section that you have. Okay, so but anyway, we'll come back to this. So now we go to talk about some concept of understanding the objects we use in Etabs. Okay, you are modeling a finite element model. It consists of many objects. Yeah, so we will go to this theory. So there's no hands-on required. So all right. So in short, in a very simple way, you have the three kind of object in Etabs: the point, the line, and the area. The point is the joint. Yeah, and the line is a frame that can be a beam or columns, or can be a beam column, or even a brace. And the area is for the slab on the wall. Okay, just for your information, some people like to use step 2000 because step 2000 has another three kind of element. We have a solid concept, solid. Yeah. We also have a tendon and cable, which is not available in Etabs. Yeah, that's the different element that you have. So let's understand what is the object for. So a point object is the end of a line or the corner of an area, right? You can use it to put support, put restraint, and you can put it to apply load. The connectivity between elements are all through the nodes in finite elements, yeah? Okay, there are some other things that you can assign, the rigid diaphragm, the panel zone, to account for the steel beam and steel column joint, yeah? Ground point spring and all this stuff, and you can read this easily. So, going beyond, we have the 1D object, which is the line element. It's called 1D because it's only have one dimension, the length. So as I show you, a column actually is just a line. Yeah. So it's used for beam, columns, braces, which is your braces, yeah, or a null line. A null line is a line with no property. Somebody asked me just now about how do you apply a partition load or brick wall load on your slab. Yeah. So load can only apply onto the nodes. Right? So if you have a floor, if you want to account for a line load, you may need to put in a line to accept the line load. So one way is if you don't want to change the property of the slab itself because you only have the slab, right? Not beam, right? So you put a null line. And null line is not a structured object, it must be sitting on a structured object. But I also tell the same person that usually for partition load, for brick wall load, we always apply as a UDL load. We estimate it and apply as a UDL. It's a lot more manageable, a lot more efficient that way. Yeah. So in Etabs, everything is automatically defined. Horizontal is beam, vertical is column, slanted is brace. Things are changing. Yeah. The architects now is very fancy to have a column that is not straight. Many this kind of building, and later we'll talk about how do you account for this. It still can be a column, but you just need to know that it will change the behavior of your floor. Yeah. All right. So they have many things you can assign to the line objects. Yeah, basically the properties and the releases and all this stuff, which is important that we will see later. Yeah, and then we talk about the 2D element. It's called 2 dimension because you have the width and the length. Yeah, and you have four nodes or 3 nodes. Important. If you study finite element before, you know that there are different elements. The higher order elements. In Etabs, you only use the very basic one, which is called the Q4. Q4 is a 4-noded element, or the CST, the constant strain triangle, which is 3-noded. These are the only 2 that we need. Why do we need to have higher order element? There is a Q9 where 1, 2, 3, 4, 5, 6, 7, 8, 9. So each element has 9 nodes. It's higher order. The whole idea is with a higher order element, you can use less element to achieve the same job that you have. But because we can accommodate very many elements, right? So there's no need to go higher order. What you need to remember is you must only use 3 or 4. Okay? However, we prefer 4. We always prefer 4. When we do the meshing whatsoever, we always try to use 4. Very, very simple. In the concept, in the Q4 element, this is one element, 4-sided. Need not be rectangular, as long as it's 4-sided, yeah? In the right proportion. Numerically, in finite element concept, this point, this point, this point, this point, this 4 point is called the Gauss point. Gauss point is theoretically where the result is exact, is correct. Other than that, you have no results. So now, and then if you use a triangle element, CST, 3-noded, right? Only have one Gauss point in the center. That's why it's called constant strain triangle. Okay? So if you understand these two, now look at the table. If I use only one Q4, I have 4 points that is correct, right? Think about the behavior of this table. When I load it, the chances of me capturing the right problem in the 4 point, quite close, right? I mean, it's possible that I only have this 4 point, which is almost the same for a rectangular table. But if I change to 2 triangle, I cut it into half. I have one Gauss point here and one Gauss point here. To have that behavior to be constant there and constant here is not easy, right? You cannot capture this bending because it's bending this direction, right? So I must cut this way and cut this way to have at least 4 elements just to capture the table behavior, right? The more element is better. So that's why we always try to use 4-sided instead of 3-sided. To you as an engineer, you just need to understand that you can model a floor of as many sides as you want. Yeah? For a structure floor, which is shell and plate, which I will explain more later, you have to mesh. And just make sure that after meshing, there's no element that is more than 4 sides. It's 3 sides, 4 sides. Not an issue for you anymore. Later you will learn that Etabs do automatic meshing. We have something called the global mesh, which is very, very powerful. Yeah? So you don't have problem anymore. The only problem we have is like an old professor. In the old days, Etabs meshing is not so powerful, right? So if you're not careful, after you apply the meshing technique that you apply, you may end up having some element with 5 sides. Because you say cut there based on this node and all stuff, and then some element are 5 sides. So this 5-side element is called illegal element. When you analyze, it will disappear. You get thrown away. So suddenly after you analyze it, why I have a hole right there? So that is the reason why. Because you accidentally mashed the floor into a 5-sided element, which is illegal. So because of this, some old engineer get smart, and so he tell all the junior engineer, don't do anything more than 4 sides. So you start drawing every piece. Actually, when I ask you to say don't draw anything more than 4 sides, you will end up everything is 3 sides. Because that's the easiest to fill up any shape that you have, right? Which again, come back to the same question. 3 sides is not as good as 4 sides. But he also told you that after you do all your elements, you need to match it also. Because when you have a 4-sided element, when you match it, it will become better. Yeah? Alright, that is something about mesh convergence. Right? So these are the concepts that you need to understand. So basically, that concept is old. Don't draw element based on 3-sided and 4-sided. It takes a long time. It also takes a long time to create an analysis model. The reason why I said, okay, basically in the old days, if you start to draw things manually, many pieces, you mesh it again, many pieces, you have done all the meshing. So in that case, if you use that old method, you must tell Etabs not to mesh anymore. Because if you don't tell Etabs, Etabs doesn't know. Etabs is programmed internally to look at every shell and mesh for you if needed to the best it can. Imagine the way the modern engineer do the job. I will draw my floor based on the property of the floor and the loading. What do I mean by that? I have every floor in this building is 150 mm thick. So I have only one kind of floor, right? But the loading is not the same. I have office here, I have workshop there and all that stuff. So if I have only one big piece of slab with many sides cover the whole place, I cannot load efficiently, right? I will have to use patch loading, which is very tedious. So instead, I look at the whole floor plan, divide my floor into 5 pieces based on different usage. I can load differently. So that's the key idea. I only have 5 pieces, and then Etabs will go in and say, look at these 5 pieces, and I will mesh for you accordingly. That's what Etabs does. So compare the 5 pieces to the finer pieces that you draw by small piece by small piece, right? That will take, if Etabs apply the routine to check every slab before it analyze the mesh for you, it will take a lot of time to check all these things, right? Even though after it checks that nothing needs to be done, move to the next slab. Yeah, so it's not advisable for you to draw many small pieces. Instead, always remember, you draw floor based on usage, because of loading, and based on property. Okay, that is the key concept, huh? All right. And we talk about the degree of freedom. Basically, in a full finite element analysis, yeah, each node has 6 degrees of freedom. 3 translation, x, y, z, and 3 rotation about x and y and z or z axis. Right? So that is how showing you the M2, M3, and then strong axis bending, everybody know, right? I don't think anybody has to explain. And then we can have different kind of loading on the frame. But typically in Etabs, most of the time you don't load the frame, but in your steel maybe different. Because when you like a purlin, you don't model the roofing, right? So you have to find out the loading and apply to the purlin load, right? So these are this. So you still have to do loading. But in a normal building like RC, most likely the only time you load a beam is when the beam is supporting a wall. Or else you use the floor to translate the load to the beam. And for temperature load, just for your information, Etabs can only account for load that change the length of the section. Means the temperature change that cause the element to expand or contract. Okay, that is one effect. However, imagine that you have this roof. This roof, yeah, sun is shining here. This is hot. Inside is aircon, cold. So expand, contract below, right? It's bending. Yeah, that effect is called temperature gradient. Can only be done in step 2000, not in Etabs. Yeah, so if you need to check, if you need to capture temperature gradient, then you need to look at step 2000. Okay, so now we come back to look at the concept of modeling the frame system. So draw frame object, all this I think you guys know. We didn't talk much, yeah. And release, you know, right? You know how to do releases, right? Yeah. So the only thing to highlight is you cannot release torsion at both ends. Yeah, if you release torsion at both ends, it becomes axial. Yeah, it's not stable. Yeah, right? Okay. And then extrusion is a very powerful command. Yeah, later I will show you when we have a chance to go to the lab again. So you can extrude a joint to a line. You can extrude a joint to a line. You can extrude a line to an area. Yeah, and then it's in step 2000, you can extrude an area to solid. Yeah, so that is and the extrusion can be linear or circular. Yeah, and one of the exercises that we have is to create a ramp. A ramp can actually extrude it from a line and sweep down. Yeah, and then a circular wall going straight down. Yeah. Yeah. Okay. So, as I mentioned, connection is all through the node. Connection is all through the node. But we have auto frame mesh. So if you have a beam here, supported by 2 columns, so because it's not there, right? So it's connected. When I put a beam into this beam, So this beam, you have an intermediate node at this frame, right? So by default in Etabs, it's turned on by default, auto frame mesh at intermediate joint. So basically what it says is when you put here, this frame will actually mesh itself into two pieces and connect to this. So it's connected. Some software like Step Pro, for example, may not do that. You have to disconnect it and join them. So or else it's not joined. This can go like that and go up because it's not connected. But it's not a problem in Etabs. It's done automatically. However, you have cases like what I see here. When you have two crucify cross, so this beam and this beam, is it connected in the center? No. By default, it's not, because we only mesh at intermediate joint. This has this node and this node. This has this node. So there's no joint in the center, right? Yeah. So it's not connected. However, you can force it to connect if you change the frame mesh. The auto frame mesh options has another options, say frame at intermediate joint and intersecting. So that will make it connected. However, when you have a brace like that, do you connect to the center? No, right? No. Yeah. So that's why the default is okay. So you don't have to change it. Or alternatively, if you know what you're doing, I can draw this from here to here. I can draw this from here to here and from here to here, right? Make it into two sections, right? Wow, quite powerful, huh? Yeah. You see what I mean? So you can do that kind of thing. So that is understanding how Etabs works, because I physically introduce a joint, let them connect, or else I change the meshing command. Right? So that is called auto frame mesh. Yeah. Another thing is called auto frame mesh, also applied to slab. A slab, a shell has to be meshed in order to perform its duty. Yeah? Without meshing the floor, it will not have the degree of freedom to capture the deformation that you want. Right? Once you mesh the slab, the nodes you generated on the frame, right? So if I don't have the auto frame mesh turned off, then this particular one will only connect at this end and this end because there's only two nodes of the beam. But because auto frame mesh is turned on, the slab after you mesh will introduce a lot of intermediate joint, and the beam will automatically mesh itself to connect. Okay? So that is a very useful function. But now, you look at this, the left hand side. I actually turn off the auto frame mesh. So if you turn on the auto frame mesh, the slab will not be connected to the beam. So what does it mean to you? Wrong. I mean, most of my trainee will say wrong. This is wrong. I must make sure I don't do that. But for you, this may be correct for you. Right? You see what I mean? This is the beam slab system. The beam is supporting the slab, so it's connected. But you have a steel structure. You have a steel structure which is a car park. And then on top of steel structure, you have a glass. The glass is only supported at four corners. So this captures the behavior of a steel gazebo where you have a steel, but the glass is connected at four corners. You still have the stress in the glass because of the final element, but the glass is only connected at four corners. So this is the correct model for your steel structure. You see? So that is how understanding what you're doing. If you do this with the two-four connection, you are using a wrong model to estimate the load. You see what I mean? So that is important to understand. Okay? This particular thing is talk about the RC frame. Imagine that you have a 1 meter by 1 meter column and 1 meter by 1 meter beam, right? So it's a line. But actually this line of the beam, 500 is inside the column. Same thing, the beam column coming up, 500 is inside the beam, right? So if you don't account for it, you ignore the overlapping, this thing is free to flex, right? Flex, right? You can bend from here to here, right? But in real life, the first 500 is inside the column. There's no way it can flex. This one is called the rigid zone, right? Rigid zone, yeah? And not only that, the moment at the center of the column is also very, very high for the beam. It go pick up, right? Yes. So engineer always say design column to the face. Yeah, so that's what we do. So that is how you control. So you can tell me how much of the length of the beam inside the column is part of the rigid zone. I mean, theoretically, you can always say it's 1. 500 is 500, everything is inside column, cannot move. But engineer is very particular. A column, RC column has cover. a cover, right? Cover is non-structure. So if you say 1, the guy said, how can you use a cover as a structure also? So most of the time we use 0.5 or even 0.75. Yeah. So instead of 500, we have 250 as the rigid, so that it doesn't bend. Yeah. So that's what we mean, and then you can have way to it. This length is automatically calculated, so the program will find it itself. By default, if you always use the automatic calculation so that you have the rigid zone, but we don't change the length of the section that belongs to the column, inside the column. So that is by the rigid factor, rigid zone factor, yeah? So, see this? This is the example. This is the extreme example. So you use 0.5, the red segment is the one that, cannot bend. Imagine that you have a beam, pin connected. So it flex, right? Yeah. So under the uniform loading, you have this displacement, D, 100 mm, right? But now at both ends, 1 meter both ends, you wrap it, make it stronger, encased in concrete. Same beam, right? Oh, this is even interesting. Never mind. I think I bring too much energy to the factory. Anyway, so that will change the behavior. So that's how we account. That's how we account for it. So basically, as an engineer, you will see that I will always account for this added joint stiffness to be more realistic in my design. Yeah. So this is more for you. I told you in the morning that your beam doesn't go into the center of the column, right? So to account for that, you use the panel zone. Panel zone will adjust the joint stiffness based on column only, for example. Because the beam is outside, right? At the flange, right? Stop at the flange. The center of the beam is here. Yeah. So it stops at the flange. This is the flange, this is the flange. So this whole joint stiffness is based on column only. However, very, very commonly in this kind of situation, because of the high shear deformation, you put a double plate. You weld a steel plate. Right? You can see some of, I think some of them have, yeah? So that's called double plate. We also give you a way to specify, I have a double plate which is 16 mm. So it will adjust the stiffness accordingly to account for it correctly. All this will have effect on your joint moment, yeah, and the building displacement. So this one is for steel. Frame insertion point, okay. Numerically, we always say connect, center line. In any structure that is steel structure most of the time, the line that represents the beam is in the centroid, right? So it's connected. Think about RC beam. RC beam is always below the slab, right? So actually the insertion point, what you see here is if you have a cross section, yeah, we say top center, top right, top left. Center, right, center left, yeah. Bottom center, bottom right, bottom left, right? And then this is if double symmetry, this is the centroid, this is the shear center, yeah. Okay, so these are the cardinal point that we have. However, when you join the thing together, yeah, imagine, okay, let me just go to the next slide. A column. Column is always wider on one side than the other, usually not the square column. Even the IW section that you have is also longer than the width, right? So, sometimes your beam doesn't come into the center, in this case. So remember I mentioned to you that the column on plan is only one dot. Yeah, so this is the column, right? But actually, the only thing that represents it is this dot in the center, right? Right? So if my beam is coming in, I should connect here. It's called connected. But sometimes this is very wide. I want to put my beam on the side. So coming is here, right? Let's imagine that coming here. This dot and this dot never connect. So is it connected? No. It will fall off. It will not be connected. But I know I can put the beam like that. It will not go away, right? Because you have a ridge section here, right? Column is like that, right? Or the beam is actually sitting somewhere here, right? Center here, right? So a more explicit way to account for this is to create a link. A link is a connecting between 2 points, and you can specify the behavior accordingly. But in Etabs, we simplified it. You don't have to do a link. Instead, you still put draw the beam to connect to the center point of the column, and then use the insertion point offset to move it. Okay, so that will account, they will create the link for you automatically, and you account for the effect. Yeah, okay. One thing to remember, steel is not so particular. I mean, you look at the whole line of columns, the center line of the column all in line, right? Even when you move up to the outer column, it's still in line because you use the same size, right? But in concrete building, tall building, encased concrete, for example, the column size can change, right? But they all have to fix that in such a way that this thing must stop at here, right? So this is here. If I have a column this way, it's like that, right? So if you're not, I'm bringing you another concept right now. Don't always think that I must put the column in exactly the same place like the architect one. Because if I do this one here, this column there, so these two lines and this column, they're all not straight line. And then I need to run a straight beam. Yeah, so you have to do all the offset and all the offset. Chances are, most of the time, you will mess up. The model unstable, cannot run, right? But based on our experience, you can actually put all the column in one straight line. The effect will not change that much. But you can ensure that you have a good model. Yeah, that is what we usually do. Yeah, so that is something that you need to remember. We will see this effect later. And this tension only member is big. You used that before, right? It works for you? Good, right? It worked, right? The only thing you need to remember is tension only member is non-linear. You need to use a non-linear static load case. Do you use a non-linear static load case?
Yes.
Yeah, okay. You have to. Yeah. So when you have a non-linear load case, means that you cannot do superposition. It's not a problem for you because you're doing direct analysis method anyway, right? Because direct analysis method always have to explicitly define for each combination, right? Yeah. So that is not a problem. But in the past, when we don't do direct analysis method, when you do effective length, you actually do linear analysis. Yeah. So if you do linear analysis, this effect may not capture. What do I mean? Let me explain a bit more. When you design a frame, a factory, the factory has live load, has dead load, and has wind load, right? You actually, in a linear analysis, not direct analysis, I'm talking about typical analysis of a factory building, using the effective length method, you do a linear analysis. You actually don't analyze the building to take wind, dead, and live together. No. You look at the effect of dead load, you get one force out. Look at the effect of live load, you get another force out. And the third is wind load. Now imagine that I said I want to see the combined effect of dead load plus live load. 1.2 dead load plus 1.6 live load. You just get the moment from dead load times 1.2 plus the moment of live load times 1.6. You add them up. This is called principle of superposition. Right? So that only works in a linear system. Right? But not in a non-linear system. What do I mean by that? Okay? So if you see this thing, yeah, imagine that I have load coming from the left, I have load coming from the right. Right? And this is non-linear because it's tension only. Right? Right? Okay? Yeah. So if you look at the next screen, from the load coming from the left, this is in tension, this is in tension, this is in compression. Right? Compression we have no load. Right? Now, for this particular case, load coming from here. This is in tension, this is in compression. Compression have no load. Right? Yeah. Right? Because zero compression, tension only, right? Yes. Right? So if you use principle of superposition, when the four is all together, you will add this plus this, right? Then both of them have tension, right? That's what you get by principle of superposition, right? But in real life, it's the top. If you put two together, the brace is not working anymore because it cannot take compression, right? So it's actually zero load. But if you use principle of superposition, you have tension and tension add together, so both of them in tension. That we can explain why we cannot use superposition when you do nonlinear. You have to explicitly define for the loading, and usually it's even one step further. You have to account for the step of loading also. Like earthquake, you load it with gravity load first before you start pushing it. Yeah, alright? This is another topic that is quite important for RC people, but maybe not so for you, just to get that feel. Torsion is always a bad thing. Even for steel, torsion is still not good. And try to avoid torsion. You arrange your frame to minimize torsion, right? But in the RC world, for engineers who design beam, we try not to design for torsion, and what we do is we reduce the torsional stiffness to only 10%. 10%. 10%. No. But basically what we're saying is that the beam under torsion will crack. After it cracks, the stiffness will reduce. Just like in RC beam bending. Beam will have crack, the crack factor is 0.35. So after it cracks, you have only 35%. Column is 0.7. I mean after it cracks, you have only 0.7, 70% of the stiffness. Alright? Okay, basically in seismic design, it's unreasonable to assume non-crack section. Concrete always crack. And the load distribution based on the stiffness. So if you assume everything is non-crack, right, then the distribution is not correct. Because why? In a building, look at the beam. Beam have no axial load, right? Only a bending, right? Yeah. So it will crack accordingly. But column will crack less. Why? Because even though it has bending, it has compression load from the gravity load coming down, right? So it cracks less. So the reduction in stiffness is only 30%, become 0.7. The beam is 0.35, it reduced by 65%. So now when I adjust the stiffness accordingly, my load distribution will be more realistic. That's what we use the crack section property for. Alright? And for beam, for torsion in beam, we only use 10% because from all the testing that people have done, if you crack a beam by torsion, the moment you crack, the torsion stiffness reduces very, very much to only 10% behind. So that's what we do. But in general, the first time you hear the word 10%, you will say, are you sure or not? You reduce by so much, right? But I'm telling you that, don't worry. The torsion comes in two forms, equilibrium and compatibility. The equilibrium torsion is always captured. Yeah? What do I mean by that? So imagine that this slab bend. This is the beam. When this slab bend, one way, yeah? This one will rotate, right? Yes. So the rotation is caused by compatibility in deformation, right? However, if this is a cantilever slab, I load it, this one will turn down, right? And actually, the whole thing is for equilibrium, right? So that is called equilibrium torsion. So we can show you very easily that if I have a beam slab system like that, you see, if I reduce the stiffness of the thing, the torsion will reduce significantly because most of this torsion is called for compatibility. You still capture the equilibrium. Now, if I have a pure cantilever, whether I reduce or don't reduce, the maximum torsion is the same because all this torsion is for equilibrium. So reducing the torsional stiffness of a beam will not reduce your equilibrium torsion. Yeah, that's what it means. But I want to show you something. See, they are under the same load. The only difference is this one is stiffer than this one. So under the same load, this one will rotate more. This one will rotate more. Okay? Right? So, may not happen to you that often. In the RC people, come back. In the RC people, they always have problem designing for cantilever. Your balcony is cantilever out, right? Yeah? So they always say, hey, cantilever displacement doesn't work. So when that happens to you, what do? You do hand calculation. And you calculate. It passed. Don't doubt my calculation of my first class honor one from a top university in Cambodia, for example. Yeah? But the thing is, so for these two cases, if I ask you to calculate the cantilever displacement at the tip, you will give me the same answer. Right? But numerically, it shows you two different displacements. The reason why, because your hand calculation is based on fixed cantilever. Fixed cantilever, right? Fixed here. This beam, these two cantilevers left, the fixity is the torsional stiffness of the beam. So both of them have different stiffness in the joint, in the fixed joint. So it has different notation. So your calculation is not correct because you don't account for the flexibility in the support. So that is another concept you need to know. Sometimes we always trust our own calculation, but your calculation may not simulate the actual behavior because you have a simplified approach. Yeah, all right. So that is something to know about. And this is another very common thing. When you look at a car park, I mean, you don't have that many car park, multi-story car park in Cambodia. In Singapore, we have a lot of them. And car park, we try to maximize the number of level, yeah, headroom. So your beam usually is fair. Yeah. How do you classify a beam as a beam and it's not a slab? Same thing. How do you classify a column as a column and not a wall? The simple rule of thumb is one side is no more than 4 times the other side. 4 times is the maximum, right? So if the beam is 500, you can have 2 meters wide, right? That is the limit. But many people ignore this. Even you have 3 meters, you still call it a beam. Why? Simple. You put a beam, reinforcement come out already. By Etabs, you don't need to do anything. The reason I say that is not correct because when you have a wide beam, it doesn't behave like a beam. It's not one way, it's 2 ways. It's 2 ways. Yeah, so you have to be careful. And a deep beam also has a problem because as the beam becomes deeper and deeper, it becomes more like a wall. The shear is not constant across the section. So if you look at these 2 beams, one is modeled as a beam, 2 meters by 500. Another one is modeled as a thickened slab. Yeah, you will see the bending moment of the beam and the bending moment extracted from the slab. Depends on how you look at it. Very similar, but the distribution is different. Yeah. So if you look at the stress contour, see, in the center for the shear, our moment contour at the hogging moment is much higher in the center. So the effective thing, let's imagine that you have a 2 meter wide slab, a beam, 500 deep, even though it's still classified as a beam. But after you design, they ask you to have 20 T 20, for example. You distribute equally, right? But based on numerical analysis, the center part is highly stressed. So you should have more bar in the center and less bar as you go away. Yeah? So that is an effect that you fail to capture if you use a beam. Yeah? That is just to show you, and both moment and shear will be distributed differently. It's always highly stressed at the center and less effective as you go out. Just to understand, not everything is simple for you as an engineer. We need to use an element that is appropriate for the behavior that you expect. It's much more reasonable to use a thickened slab, and now with Etabs Ultimate, it's not an issue anymore because you can design the slab accordingly and get the reinforcement that you want. Okay, so now we go back. We are talking about 1D element and 2D element. Now this one is 2D. Okay, but that 1D element and 2D element are basically just about the geometry, right? Look at the frame. A frame subject to the coupon test, tensile test, is a 1D experiment, only one direction, right? But the frame formed into a truss like you have, it's a 2D structure, right? But it's still form of 1D, right? You can do a space frame, right? It's 3D, but it's still 1D element, right? So it all depends. Even I-beam that you have, I-beam, white flange beam that you have, for example, the best element that you need to use for I-beam is actually a line, right? But sometimes, instead of using a line, I would change it to a shell. 2 shell, 1 shell at the flange, and then wrap, and then another two at the bottom. So I have a shell to form an I-beam, right? And I analyze it. Why I do that? Now I can see the buckling of my top flange. Yeah? If I do a line element, I cannot check the buckling. I can only calculate, yeah, just estimate. But now I can do that. But if the I-beam is very big, huge one, the girder, right? I may change it to solid. I can see the top fiber actually yield first below and then migrate down. So you as engineer, we need to choose the right element. Yeah? I have an engineer who called me up and said, I need to use solid element in my bridge. Yeah? But solid element doesn't seem to give me the result I have when I put tendon. Yeah? We don't, no. Solid element, we don't formulate the time-dependent property of the solid element. it's not inside, but shell we have. And he said, the solid is the best element I have. I have to use solid because it's better than shell and better than frame. Think about it. A fat beam, you also don't want to model as a fat beam because it's simple to do a line, right? Right? Yeah. Now you change the fat beam to solid. In fact, when you do solid, it's very difficult to understand the stress. Anybody who do solid, we always use the Voronezh stress. Voronezh stress is used in the allowable stress design, non-directional. It just gives you the magnitude of the stress. And make sure you don't exceed the limiting stress, that's all you do. Yeah? So not necessarily the higher order element like 3D is better than 2D, 2D is better than 1D, depends on the usage. Okay? Now, this is the big part. We now move on from frame to shell. Yeah? What is so complicated about shell? You have the 2D effect. And now we need to understand what is the shell behavior. When you have an area like a floor, subject to gravity load, this thing will bend, right? It's called out of plane bending. A plane bend out of plane, right? This is the property of a plane. Plane. If you have a retaining wall, retaining water, bend this way, it's also plate bending, right? So out of plane bending. If you have a shear wall, you subject load here, you bend this way, remain plane, right? That in-plane bending is a property of membrane. So membrane has in-plane bending, plate has out-of-plane bending, yeah? Shell is nothing but membrane plus plate. So shell can bend this way, can bend this way. So everybody clear? Okay? Now if you're clear of this concept, I ask you, what is the thing that you need to use for your floor? When in doubt, shell is always the best because you can do everything. But most people will say plate because you are thinking in terms of gravity load, right? But building floor include notional load, include wind load and all that stuff as in-plane bending also. So shell is more appropriate. Yeah. However, in Etabs, you can use plate plus rigid diaphragm, which is another concept that I will bring in later. Yeah. The rigid diaphragm take care of the in-plane stiffness. Okay. And when some people in the early days we also use membrane for floor. Membrane has no out-of-plane stiffness, right? But membrane floor in Etabs actually switch to another mode. It does what we call the load transfer based on virtual membrane concept, U-line concept. Just like your deck, it's actually a membrane. You have no stiffness, but it transfers load to your supporting beam for composite beam design. Okay? So if you use plate or shell, it's termed as structure slab, then you can activate the thick behavior. The thick behavior actually turn on the deformation. Yeah? Account for the shear deformation. Okay? Means that my formulation will include the shear deformation. Okay, what does it mean by that? Now look at a normal beam, a 300 by 600 beam. 300 by 600 beam span 10 meters. Go and look at Timo's or stress and strain and find the full equations to calculate the displacement at the center of the beam. You'll see the full equation is so long, one part, another part. First part is for bending, second part for shear. For this 300 by 600 beam, the shear gives you 0, all due to bending, flexure deformation, right? But when you increase the depth from 600 to 2 meters, still 300 wide, do the same calculation again, now you see the shear part coming a lot of value. That is deformation due to shear. Yeah, so that is what you mean by shear deformation. But one thing to understand is not necessarily thick is just a number. Don't ask me, Mr. Chu, what is thick? Tell me. So anything more than 1 meter is thick? Then I will, every time I have a 1 meter and above slab, I will turn on the thick. If anything less than 1 meter, I will say thin. That's not true. I can tell you that my 1 meter thick slab is not thick because it spans 20 meters. I have a big stadium floor that spans 20 meters. So 1 meter thick is not thick. But I can tell you this slab here, yeah, 200 mm thick is very thick. Why? Because it spans only 400 mm. The thickness is half the span length. So it's thick, right? So that is how we understand. So when you have an aspect ratio that can result in shear deformation, you use the thick formulation. or when you are subject to high shear, like a rough foundation. Column has high shear, right? So you use the thick formulation. Okay. Now this come back to the part whereby we talk about your bending. Remember we talked about M11, M22, and most of you will think M11 is bending about M11 use the right hand rule, right? And I told you it's wrong. Okay? So this is the part, my favorite part. Right? This clear up all the reason why you always choose the elevator, because you are so fixated to the vector that represent the beam moment, yeah? Or column moment. So you look at this diagram. Look at this diagram. 1, 2, and 3. 1, 2, 3, just like the right hand rule, yeah? This face and this face is the perpendicular face to 1. Yeah? The one in front is positive, the one behind is negative. Positive one face, negative one face. Same thing, 2 is going that way. 2 is going that way, positive and negative. Right? And then 3 is going up, bottom is negative, and then the top is positive. Can you visualize this? Can that? Yeah. Right? Now I go to the next slide. Just read the first one. It actually said, I'm not talking about force, I'm not talking about moment yet. I'm just talking about stress. The stress S11, yeah, is actually the direct stress that's acting on the number 1 is the face. So S11, the S1, the first one, say the stress is acting on this face and that face. Okay? The second one is the direction. The stress is acting on this face and this face in the one direction is S11. So same thing, S22 is this face and this face in that direction. You can see, right? So what is S12? S12 is acting on this face and this face in this direction. In plane shear stress. Huh? In plane shear stress. This face and this face in that direction, in plane shear stress. S13, out of plane shear stress. Stress in this direction, this face and this face up is S13. So everybody clear, right? So that is the stress. Okay? Nobody lost, yeah? Okay? Now I take one strip. One strip in the direction of 1. Yeah? So this is a 1, 2, 3, right? This is negative one face. This is positive one face, right? So the stress that's acting on this face is called S11 and S11, right? Right? So if S11 is constant across the thickness, stress times area become force. Constant F11. F11 is an axial force. However, the stress can change from top to bottom. The top is compression, the bottom is tension. Right? Yes. That become M11. That's why it's called M11. 2 number. M11. So what you need to know is both of them are S11, but the varying stress across the thickness causes M11. Now, M11, we have tensile stress in the 1 direction, right? Right? So if the tensile stress is this direction, where do you put your bar? The rebar will be in the same direction, right? So if I put my rebar this way, my bending is which way? Must be this way, right? Yeah. If I do this way, the rebar doesn't do anything. It cracks the slab. It makes it easy to slab. It's this way. So M11 has the rebar. Let's imagine this is 1. Yeah. M11 has a rebar in this direction and it's bending along the same direction. So that's how we remember it. So M11 requires rebar in the 1 direction, so it's bending along 1 direction. M22 is the other direction, right? So that's how you remember. So if you go back to the screen before, this is 1, M11 is this way. Yeah? This is 2, M22 is this way. But this is another one, M12. Twist, twist, twist. You don't do twisting reinforcement. Nobody knows how to do this twisting reinforcement. So what we do is we modify the M11 and M22 to account for the twisting effect. That is called wood armor formulation. Yeah? Wood and armor come up with a way to account for the twisting using M11 and M22. Yeah? So this show you the diagram for the F11 and F22, F11, F22, F12, yeah, and M22. Okay, this is the one that confuse you. When your professor teach you about the right hand rule, it can't imply that you use the right hand to grab the axis. Actually, it's not grabbing the axis. It's grabbing the vector. Vector is double arrow. So happen that M3, the double arrow, is parallel to 3 axis. Yeah, M2 is parallel to 2 axis. But you see, this M2 is perpendicular to the 2 axis. See this vector and this vector? So M2 is actually this way, M1 is this way, right? So that's how it confuses you. But anyway, you just remember, M11 is bending along, M22 is bending along to 2 directions. It's clear? Everybody clear?
Yes.
It's very important in RC because then only I know where to put the reinforcement, or else I will put the wrong reinforcement. For a cantilever slab, imagine this is a cantilever slab. Fixed here, cantilever from the wall. Where you put your rebar? On top or bottom? Top. Yeah, that is very important because cantilever tension is on the top. The bar is for tension. Yeah. All right. So this is a quick reminder. Okay. So let's review the loading to area. Yeah. So if you use membrane, if you use your deck, it's membrane for load transfer only. You don't need to mesh. You don't need to mesh at all, right? You just let the program does its job and then it will transfer the load for you. But if you use shell or plate, you have to mesh. Without meshing, it will not work. System engineer. You have system engineer here, right?
Yes.
It's called system engineer? Is that right?
Yeah, building system engineer.
Building system engineer, correct. So building system engineer, a lot of prefabricated or precasting, yeah? So I said my slab actually come in one piece. Or even my glass table. My glass come in one piece. You cannot say my glass cannot be meshed because it's one piece. You still have to mesh your glass in order to capture this bending, that bending, right? So meshing is important for any structure element. When you put membrane floor in the RC building, the floor is non-structure, it just collect load. And this is how it collect. It's very simple. By geometry, triangular load on the short end, trapezoidal load on the long end. If you have two-way load transfer, if you have one way, it will be like a deck. If you go in the direction of the one direction. So it's important when you do a deck on your beam, make sure the arrow drawn on the deck is perpendicular to the beam. Or else, if this is the beam, and there's a main beam there, if the arrow is this way, the load go there, doesn't go to your beam. Then your beam will say, hey, I'm not taking any much load because the load transfer is pointing to the wrong direction. Yeah, so that is what you mean by the arrow. Yeah, okay. One common thing, not so important for you because you don't do RC, but the procedure for transfer load is very simple. But if sometimes you encounter a missing beam, for some reason you have only 3 beams instead of 4 beams, this is called missing beam, right? Yeah, so this triangular load have no place to go. It's supposed to go to the beam, but beam is not there. So what Etabs will do is it push the load to 2 sides. So the triangular load become a point load at 2 ends of the missing beam. That means that this beam and this beam is under design for this triangular load. Right? So it will not work in that way. So you have, if you are a concrete engineer or RC engineer, you have to be careful. When this thing happens, you cannot use membrane. You have to overcome it by some other means. Calculate your own load and apply it, or you can use what we call a shell membrane. A shell with limited bending stiffness to simulate the membrane behavior. Okay. When you have membrane, don't mesh.
Membrane don't mesh.
It will mesh by itself. A big piece like that will become 4 pieces, and each piece will do like what we said here. The program will do it itself. However, when I say don't mesh, most people will say, I don't know what he's talking about. I am doing finite element, how can I don't mesh? Your membrane is not a real finite element. Membrane is a virtual membrane, right? That's why I say don't mesh. But as I said, everybody will start meshing. So we have a problem. Either, if you start meshing, you have a lot of missing beam, all the load transfer is all gone out of the case. So actually, CSI has decided if you mesh a membrane, I will do a shell membrane. Basically, I will do a finite element formulation for your membrane, yeah, with no bending stiffness. So the load transfer is through finite element, not the load like not the U-line kind of load transfer. Okay? So this shows you how you can transfer load to the shell, and all the loads will go to the thing, and then you get the load into the beam. Okay? So this is a good time to talk about meshing. How do you know your meshing is good? Even for if you use a deck, you don't have to mesh. But sometimes we have a case where you have a roofing steel plate and all that stuff, you need to mesh, right? How do you know your meshing is good? A general rule of thumb for building typically is 1 meter. 2 meter, 1 meter, 1.5 meter, these are the range. I will start with a 2 meter to start with, and then I will refine to 1 meter if I need to. But how do you know 1 meter is better than 2 meter? Basically, look at it. If I have no meshing, only 4 corners, all load go to the column, right? The beam is not taking load. If I mesh it 4 pieces, I will have 1 point load here, 1 point load here, 1 point load here, 1 point load here, right? You know this is trapezoidal, this triangle, right? The point load cannot capture the trapezoidal load nicely, right? So that's not enough. But if I have 4 element, I will have 3, let's say 3 point load here, right? 3 point load can simulate all kind of load. So again, the minimum number of elements per beam has to be 4. That is the rule of thumb that we use. Yeah? And how do you know 4 is enough? Your goal is to find the bending moment of the beam, right? You see what I mean? Right?
Yeah.
So use 4 elements, check what's the bending moment. From 4 elements, you change it to 6 elements. Does it change a lot? If it doesn't change a lot, means the 4 elements is good enough. Like for example, from 2 to 4, right? 2 change to 4, bending moment change a lot. So 2 is not enough, 4 is good, right? So now 4 change to 8, bending moment doesn't change much. So this is called mesh conversion test. Means that from 2 meter change to 1 meter, it changed a lot. So I should use 1 meter mesh. But from 1 meter mesh, I change to 0.5 meter mesh, doesn't change much. So there's no advantage to go to 0.5 meter. When you have more element, you need more time to solve the equations. Yeah? But it doesn't give you benefit. How do you mesh your floor, or shell, or wall in Etabs? This is called mesh convergence. Yeah, mesh convergence. Meshing. So since Etabs 2013, we have a global meshing. Basically, global meshing means you just tell me what is the mesh size that you want to control. 2 meter, 1 meter, 0.5 meter, or 1.2 meter. You tell me, I will mesh for you automatically. So that's what we usually use. In fact, all my customers use it. But you do have a choice. If you want to refine the thing, you have what we call the external versus internal, or manual versus auto. Yeah? External means manual. Manual means that I have this table, this table. In order for me to model this,